Welcome to the fourth episode of Apple Finch Pudding, your gateway into the world of science. Today's co-host is Thomas Lebbe, a PhD candidate in macroeconomics with a passion for history. Welcome, Thomas. How are you?
Hello, Jeroen. Thanks for having me. I'm doing great. How are you?
I'm fine, thank you. So, a passion for history. What do you like about history so much?
Well, I think the nice thing about history is that it connects all aspects of society. It connects culture, sociology, economics all together. And basically, if we want to learn about these aspects in our current day, history is a good case study. So this is why I'm interested. I'm also a social scientist. So
yeah, you studied political sciences, right?
Yes, that's correct. I studied political sciences, bachelor's and master's, and then I did a master in science in economics and a research master in economics.
Okay, so you have done a lot of things.
Yes, I've studied too much, basically. It's not optimal.
You can never know too much.
This is true, but you can study too much. Socially speaking, I think this is not the optimal solution.
It's not socially acceptable or something.
Neither. No, not at all.
If I'm hearing correctly, that's actually your main passion, like how social interactions work, both economically, politically, and also historically.
Yes, you're absolutely right. I like to think about how people behave, and especially in groups, because individuals have certain patterns, but in group context, these might differ. You know, people are different, they're heterogeneous, they act in a different way. So policy has to be targeted at the biggest forms of heterogeneity, and this might imply different policy aspects than you might expect looking purely at an individual. So this is important to think about. People say, oh yes, but I behave in that way. That's fine. But for policymakers, this is not the right framework of thinking.
Yeah. And what level are you looking at? At the level of a country or a continent or even global politics?
Well, you could look at the global politics, but I'm a macroeconomist, more specialized in fiscal policy, and most fiscal policy is made at the national level. There are some exceptions, but I target mostly nations, let's say.
Yeah. And fiscal policy, what does that include actually, or what does that mean?
So basically, it means all kinds of schemes of subsidies, taxes, transfers from one group of people to another. So basically how the government functions and how the government gets its revenues and its expenses.
So like also taxes and social security and all that stuff?
Of course, it also includes, for example, the pension system. It also includes the green taxes that we are now willing to put on, those carbon taxes that everyone's talking about. So it's very broad.
Okay. And what do you prefer? Because you're doing a lot of different things, but it's all going to the social aspect. And what view do you prefer? Do you prefer the political view or the economical view or the historical view, or really the combination of all of them?
I will confess, I hate to say it, but I prefer the economical view. I think this is a bit of cheating, right? It's also the distinction between social sciences and the more natural sciences. You have exact questions and more exact answers. The more you go to the social science, the less exact the questions become, the less exact the answers become. And economics is somewhere in between. And I am happy that they don't have these ambiguities all the time. So,
okay, but there is still a lot of overlap, I think, with economics, because economics is driven by people. So people have social interactions which affect the economy.
Oh, of course. And it is still a social science. I would never claim it to be an exact science. I don't pretend anything of that sort. So you're absolutely right. But let's say it like this. It's more quantifiable than other social sciences. In the same way that you could say that sociologists are also more quantifiable because they really put it into numbers. And this is an aspect that I really like.
Okay. Well, I guess we'll move now to the more quantifiable sciences. Today's scientist is Marjolein Vanoppen, a senior postdoctoral researcher in environmental technology at Ghent University and communication manager at Capture. Marjolein finished her PhD in 2016 and immediately started combining her research with science communication. This joint enterprise of research and science communication has led to the publication of her first book in 2021, entitled Weg van Water, or loosely translated, Loving Water. Marjolein, thank you for joining us. How are you?
Thank you for the invitation and for researching me this well. I don't think I sent you any of that information. I'm doing well. The sun is shining today, so life's good.
Okay, that sounds very good. I suggest we're going to dive right into it. So my first question is always for a science joke or an anecdote or a fact. And this is a question for both of you, but I will start with Marjolein. So Marjolein, do you have some kind of fact or joke?
Yeah, the thing is, it has nothing to do with water, but it's something that changed my perspective when I look at science and especially history. And that's the fact that when you think of Cleopatra, you think of Egypt and the pyramids and things like that. And what I found out a while ago is that Cleopatra actually lived closer to when the first Pizza Hut was built than to when the pyramids were built. Like the Great Pyramid, the Great Pyramid was built around 2500 BC. Cleopatra lived around 30 BC. And the first Pizza Hut was opened in 1950, let me look at it, 1958. So that's about 500 years difference. Okay. I thought that was really cool, and it really puts into perspective how you think about things.
Yeah.
So random fact, but I like it.
Yeah, it's a really cool historical fact. Something that Thomas will like as well, because he loves history. So.
I love it. You have gained my heart and my love because of this. This is really, and also it goes perfectly together. I'm an economist, by the way. Like human evolution, it follows like this, increasing and faster. So like in between Cleopatra and the pyramids, it was like slowly moving, and then it increased in speed, the development. And you can also see this with population. Like if you look at demographics, it's exactly the same.
Yeah.
So your anecdote perfectly mimics that idea. So I love it.
Okay, that's great. And Thomas, do you have a fact or a joke?
I have some kind of a fact, but maybe it's going to be a bit of a downer after the uplifting remark from before. I'm a social scientist, and I think we should always be a bit more critical about ourselves. So I've looked this up when I started studying economics, and apparently 1/3 of all articles in social science never get cited at all. And this is based on Web of Science data.
1/3, that's so much.
That's a lot.
It's a lot. So basically, if you do your PhD and you write articles and it gets published, that's just the beginning, basically, and that's kind of sad. But in essence, Dalia Remer nicely puts it and said it's because the availability has also increased, so it has become a sort of coordination problem. In the past, when they were more cited, relatively speaking, there were in absolute terms less papers. So basically, it's a normal evolution of time.
Yeah, right now it's hard to get on top of any specific topic, because if you want to read all that's out there, you have to read all day.
Exactly.
Yeah, it's true. But this is also a good advertisement for science communication, because that's a different way of getting your name known. And I have noticed that people know my research not because they found my papers, but because they know my name and then look at what I do and then find my papers.
You found a loophole.
Yeah, shortcuts.
Yeah. I actually have a horrible joke for today. You have a physicist, a biologist, and a chemist, and they go to the sea for the first time. And the physicist sees the waves and is really intrigued, and he wants to study the waves. And he goes into the sea and he starts swimming, and eventually he doesn't return. He's never seen again. So that's a bit sad. But the biologist is also really intrigued. He sees all the sea life and he really wants to see it. And he also goes in and never returns. And the chemist takes his notebook and starts writing his observations. Biologists and physicists dissolve in water.
I mean, he's not wrong. Eventually, they probably will.
Yeah.
In the long scheme of things.
Yeah. Okay, so Marjolein, you're an environmental scientist, but how would you describe the field that you're working in?
So the research group that I'm involved in, Paint, Particle and Interfacial Technology Group, we specialize in physicochemical water treatment. So mostly people know that our wastewater is treated through microbiology, microbes that basically eat our waste and then we have cleaner water. We don't like microbiology in the sense that we work with membranes, with activated carbon, with ion exchange technologies. If microbiology grows on those, they can't properly function, so we don't like them. I mainly specialized in ion exchange membranes. Membranes are highly technological filters. Basically, they retain certain things and they allow other things to pass. With ion exchange membranes, usually the membranes are used to only transport charged particles, so ions. Salt, also charged organics, that kind of thing. So that's very specific. My main job today is as the chair industrial and circular water technology. So that's a position at the university that's sponsored by Evides Industriewater, in which I basically try to help big industries make their water cycle more sustainable. So I coordinate industrial projects. I guide PhD students that on a day-to-day basis work on very applied science, trying to facilitate basically the translation of the work that we do in the lab to industry and make sure that that goes much faster than it used to. That's the goal.
And when you're talking about membranes, you're also talking about osmosis, or how do you use those membranes in your research?
Yeah, so one of the things that I've done some research on is, for example, seawater desalination. And the classical technology to do that, or the most commonly used today, is reverse osmosis. So I think we all know osmosis from physics classes in high school. That's the process in which a membrane that allows water to pass. When you have a higher salt concentration on one side of the membrane and on the other side, water will go from the low salt concentration to the high salt concentration. So nature always strives to an equilibrium. And if you have less salt on one side and more salt on the other, it'll try to dilute the higher salt concentration so that the concentrations equalize. And that's what osmosis is. Osmosis happens in our body as well, by the way. That's what regulates our blood pressure, for example. Reverse osmosis is the opposite of that, in which we push water through a membrane that retains the salts. So in seawater desalination, you make sure that clean water comes through, but salts are retained.
So actually by a pressure.
Yes, yeah, a very high pressure. So seawater contains a lot of salt, 35 grams per liter of sodium chloride to be exact. To make 500 liters of clean water from 1000 liters of seawater, you need a pressure of 60 bars, 50 to 60 bars more or less.
But this must be very energy intensive then.
Yes. The more salt, the higher amount of energy you need. So traditionally, up to a decade or two ago, this process cost up to 20 kilowatt hours to produce 1 cubic meter of water, which is ridiculous.
Do you have some kind of reference for that? Like for people, what is 20 kilowatts?
The average Flemish person uses 1 to 2 kilowatt hours of energy every day. Traditional drinking water production requires about 1 kilowatt hour per cubic meter of produced water.
That's a huge difference.
It's a very big difference. Now today, luckily, the technology has evolved and improved a lot. But now with our state-of-the-art reverse osmosis systems, it still takes between 2 and 4 kilowatt hours of energy to produce 1,000 liters of drinking water out of seawater. So that's still a factor 4 higher than traditional drinking water.
But a huge improvement.
A huge improvement, but we won't be able to improve that much further, in the sense that, as I said, nature always strives to an equilibrium. With desalination, you go against that striving for an equilibrium. So it's always going to cost some energy. That's the theory of enthalpy. We're not going to go into thermodynamics here, but you can calculate the minimum amount of energy you need for that type of desalination. I don't know the exact number, but it's around 1.2 kilowatt hours per cubic meter. The most efficient systems that we have now in the lab or on pilot scale achieve about 1.8 kilowatt hours per cubic meter.
You're getting very close.
Yeah, but we're never going to have a perfectly functioning system. So the 1.2, we're never going to reach that. And to go from even the 2 to 1.2 probably will require a lot of investment costs maybe, or use of chemicals for cleaning, or that last little bit probably isn't worth the investment or the effort. So it's always going to cost more energy than traditional drinking water production.
And I assume that the difference between the lab conditions and the field conditions are huge. So basically, it's not one-on-one that it will be translated in real life.
No, and that's never the case. That's one of the things that we're trying to do with Capture, by the way, is we're trying to make that transition as smooth as possible. So between the lab and real life, obviously, is a ginormous difference. In the lab, you can control every little thing almost, and it's really easy to control a lot of things. We try to mimic the real scale as much as possible in a lot of pilot installations. So much bigger installations and also much longer experiments. Because what do we see, especially with membrane technology, is in the beginning, short experiments, small experiments, they function great. They do exactly what the manufacturer says. But very fast, for example, fouling starts building up, biofilms start forming, you get clogging of all kinds of things, and things don't work as well anymore. But you only see that after a certain amount of time. And then you have to start dealing with cleaning and making sure your membrane stays functional and that kind of thing. So pilot testing gets a lot closer to that real application, but it's still limited, of course. You're not going to run a pilot for 10 years or 2 years. We've done a year before, but even that is rare.
Yeah, that's a long experiment.
Yeah, I think our longest running pilots ran for a little over a year.
That's impressive.
Yeah, it was a lot of fun.
It's something that just pops in my mind. Like, for example, when you have a shipwreck and there's a boat with survivors, they get some water through evaporation in some kind of cone system that fresh water evaporates and is captured at the sites. That is totally different from what you're doing. You don't need the pressure at all. You have a very low yield. But why would you prefer to do this when it needs so much energy if you can just get it like by solar energy?
Where are you going to get that solar energy at the Belgian coast?
That's true. That's true.
So traditionally, when people first started doing seawater desalination on a large scale, they did use distillation. So the process that you're basically describing, evaporating the water, salt doesn't evaporate, so you can get very clean, actually too clean water from that. But as you said, the yields are very low when you do that solely based on evaporation with solar energy. But what you can do, or what has happened in the past, is big distillation units where you go and heat up the water and force that evaporation. So you get a much more efficient system producing a lot more water. But up to this day, the energy demand of that is a lot higher than for the reverse osmosis systems. So those systems are still around 5, 10, even more kilowatt hours per cubic meter of water produced.
That's again a lot bigger energy demand.
Yeah, so in countries where you have a lot of sunshine and on small scale systems, that does work, and that is used, but more for like the crystallization of salts.
It's actually the inverse. You don't need the water, but you want the salt.
Yeah, indeed.
It goes back to something that you've talked about in the past, because I was always wondering, when these membranes, you go from concentrated to diluted, right?
Well, it's basically you go from average to very diluted and very concentrated.
Yes.
Yeah.
But this is perfect. This is what I assumed. But then what do you do with this very concentrated matter? Because this seems like a huge problem.
And if you can solve it, I'm sure you win a Nobel Prize.
So it is a problem?
It is. It's a very big problem. It's one of the bottlenecks of water reuse, not only in seawater desalination, but in general. And it's something we call in Dutch the wet van behoud van miserie. In English, the law of the retention of misery or something like that, where if you want to recover water, that means that you want to remove the things you don't want to be in there. And you do that at a certain efficiency. For seawater, that's usually 50%, which means I have 1,000 liters of seawater. I get 500 liters of desired drinking water and 500 liters of water that now contains double the amount of salt. But the same is true for wastewater. The efficiency is going to be a lot higher. You'll probably have an efficiency of 80% or something. But the remaining 20% now contains all the crap you don't want in your drinking water. That's a bit easier to deal with. Salts are very hard to deal with. Usually with wastewater, it's organic waste, and then you can try to make biogas from it. You can try to feed it to microorganisms. Worst case, if nothing else can be done, you burn it. With salts, that's not the case. You can't do that. So what usually is done with seawater desalination is the very salty brine, the concentrate, is redirected to the sea. Hopefully in a way where it gets mixed with the surrounding water as fast and as efficiently as possible, so it doesn't have an effect on the aquatic life there. Because the brine, as I said, it contains double the amount of salt. It's much heavier than the surrounding seawater. So if you don't mix it properly, it'll just sink to the bottom and kill whatever lives there.
There was a recent newspaper on that, or a newspaper article, that a lot of sea life was dying. I forgot where it was, because of that, because of salt water being released in the ocean.
I don't know, I'm not sure if I read the article, but if I had to guess where it is, it's probably the Mediterranean, because the Mediterranean Sea is basically a very big lake. The water gets refreshed very slowly, so there's very little natural mixing. But there is quite some desalination going on in the countries surrounding it. So there are quite some issues there. And there's two ways to deal with that. One of the first questions people usually ask is, why don't you just get the salt out and sell it or use it for something else? But the salt in seawater is sodium chloride. It's the salt that we use in our kitchen. It's ridiculously cheap. Like industrially, 1 ton, 1,000 kilograms of sodium chloride costs you 100 euros.
Really?
Yes. So there's no technology on Earth that can recover the sodium chloride from seawater for that price. Unless you can have solar energy and evaporate it. But then you need a lot of space and a lot of sunshine. So you're limited. There are other interesting compounds in seawater that people have looked at that are worth more. Like lithium, for example, is one that's been looked at a lot. But even then, it's very hard to make a good economic case, which you need if you want to have it applied in real life. So the second approach is to develop strategies to make sure that when you redirect it to the sea, it's mixed efficiently, it's mixed very fast, and it has as little impact on the environment as possible. Those are your two options.
But there will also be a lot of free riding behavior, right? Because you're talking about the Mediterranean. many of those countries need fresh drinking water. You know, it's much cheaper to just do it close to the sea than just drop it at the same spot where you got it. And, you know, just don't care about the side effects. So isn't this a space where policy could help?
Yeah, definitely. And we will need that. But to a degree, it's self-regulating in the sense that you have to also make sure that you don't pollute your own intake. If you don't take care of your discharge, you're just increasing the saltiness of your intake and making your own life more difficult. But you could just run a pipe 5 kilometers further away or make sure you discharge downstream or whatever. But yes, policy will have to play a role here for sure.
Or your Nobel Prize winning research.
Yeah, it's not going to be mine, but yes. Yeah, this is a bottleneck in all water reuse projects. What do you do with the misery that's retained?
Okay. So is that actually your main focus of your research, getting fresh water from seawater?
Actually, that was about a third of my PhD research.
Only a third?
Yeah, if you express it in amount of chapters in my final PhD.
How many chapters did you have?
6. I had 6 research chapters. 2 of those were about seawater desalination and how to make it more energy efficient.
Okay.
But that's apparently the most interesting is not the real term, but for a broader audience, that was the most sexy part of my PhD. The rest was about how to improve reverse osmosis systems for industrial applications or how trace organic components like pharmaceuticals or pesticides interact with ion exchange membranes. That's harder to sell to the general audience. So seawater desalination was the subject that was picked up on.
I actually want to jump in on that.
Sure.
Because you said something about cleaning the hormones.
Yeah, so that was the most fundamental part of my PhDs where we looked at how these ion exchange membranes that are newer than the type of membranes that are used in reverse osmosis, for example, how they interact with pharmaceuticals or pesticides or other trace organics that we now have to deal with.
When you're talking about pharmaceuticals, I actually know the answer because I listened to your podcast, but they always say that you have a lot of female hormones in drinking water and tap water. Is that true, or how much of a problem is it actually?
I'm glad you asked. This is actually a little pet peeve of mine. There's 2 ways to approach this. On one hand, you can go check if they're in there. The answer is there's a lot of trace organics in the source water that we use. Surface water, for example, does contain pesticides, obviously runoff from agriculture. It also contains hormones, pharmaceuticals, that kind of thing that comes from wastewater treatment plants that don't all remove it. I'm going to ask you a question now. Do you have any clue which pharmaceuticals are found most in our surface waters?
In our surface, so outside?
Yeah.
And pharmaceuticals?
Yeah, or pharmaceutically active components.
Can I make an educated guess?
Go for it.
Antidepressants?
No.
I would guess then actually the female hormones, but that's probably not the case.
No, the pharmaceutically active component that's found most is caffeine.
Really? Caffeine.
Yeah, and if you're really looking at pills that people take, it's or creams that people use, it's metformin, which is an active component in medications for diabetes patients, and diclofenac, which is an active component in like the gels that you use when your muscles hurt or something.
Okay.
Yeah, and we do find those in surface water. In groundwater, we do find some trace organics as well, but much less because groundwater undergoes a natural treatment while infiltrating into the soil. We don't find any of these in our drinking water. This is very well monitored. Our drinking water does not contain any of these components. That's a first way to look at it. A second way to look at it is how bad would it be if they were in there? I mean, we're very right to worry about them. We see the effects that these components can have on aquatic life. We should be careful for sure. But how bad would it be if they were in there? And there was one very interesting study from France, actually, where they looked at the components that they found in surface water and at which concentrations they would find them. And then they looked at, okay, what's the highest concentration we find in surface water? What would it mean if that concentration would be present in our tap water? And then they compared that to daily doses that people would be prescribed of this compound, or in the case of caffeine, like the advised maximum daily amount that I'm sure a lot of people exceed, but they looked at that. And I don't know by heart the exact results for all of the compounds, but in general, it said that for most of these compounds, if you assume that during your lifetime, say at least 70 years long, you drink 2 liters of tap water every day, over that period, for that whole volume, you would consume less than 10% of what is in one advised doses for a day.
Okay, so that's nothing.
Less than what's in one pill. The thing is, we are very good at measuring these compounds.
Yeah.
Our analytical machines have become very sensitive. The head of the laboratory of Pitpath told me, like, if you want us to find one molecule in a swimming pool, we can. So yes, we have to be careful, but I don't think we have to be worried.
And the result is universal for all the compounds you talked about.
Yeah, I think the 10% was like the highest number, and most of them were below that. I can send you the study if you want.
Yeah, you can.
I won't read it here, but yeah.
Yeah, no,
so
it's fine.
That was a general conclusion there. So it's good to put things in perspective, you know? I mean, aquatic life, little organisms are much more sensitive to these concentrations. For them, it's much more detrimental. But if you're looking at human health, it's good to put things a bit in perspective.
Yeah. Okay, so we talked about the seawater treatment and the hormones in our drinking water. Is there something else you do as well? That's already a lot, I know.
Well, the thing about being in science for a while, especially now as a postdoc, is I'm not in the lab myself anymore. Unfortunately, I really like gathering data and then analyzing it and then making nice graphs and things like that. But at some point, you have to move on and move up, I guess. So what I do now is I guide a lot of PhD students who all work on different topics. So, for example, there's 2 PhD students now that are working on disinfection byproducts.
What does that mean exactly? Because for me, that's a vague term.
Yeah, our drinking water gets disinfected to make it safe for us. The challenge is that it's usually disinfected by adding chlorine, which affects the organic material in the water.
Like in swimming pools, right?
Yes, but in much lower doses in our drinking water. But what it does is it doesn't only affect the microorganisms and make sure they can't be harmful anymore. It also affects other organic material in the water, and it can transform them into more harmful products. So chlorinated products, brominated products are usually an issue. Disinfection byproducts. I'm not an expert in the what's the issue part, but what we're trying to do now, or what these students are trying to do now, is try to figure out which organic matter is responsible for the formation of which byproducts. So which organic matter is actually the one to focus on when we treat the water. Because usually when you talk about surface water or groundwater, you talk about NOM, natural organic matter. But that's like a term that encompasses thousands of compounds. And there are some analytical techniques that can split that up in different categories, like low molecular weight neutrals or organic acids or those kind of things. And these students are now trying to, with membrane technology, take that source water, fractionate that natural organic matter into these separate categories, and then do experiments with those categories, looking at the disinfection byproducts, looking at biostability as well. So which fraction is responsible for the most biological growth, for example. And once we figure that out, we can also target the treatment of the water better, because different techniques can be useful to remove different types of organic matter, as I'm sure you can imagine. So that's what a few students of mine are working on. It's very interesting research.
Yeah, it sounds really interesting. And do you have some results already, or is it still very fresh?
They've been working for 2 years. So as you both know, the first year of your PhD is completely useless. Usually. No, not useless.
No, getting to learn a lot of machines. And
Carleen, Cameron, I love you. You're doing great. Everyone's first year is basically figuring out what the hell am I doing here. There's usually not a lot of valuable results from that.
I just want to point out that counts for a lot of jobs. Your first year,
Yes.
You're looking how things work.
I'm sure. So they're just now starting to working on their first research paper and stuff like that. So Carleen has done some research on how these different disinfection byproducts affect actual human cells as well. So trying to figure out which ones are more harmful. And she did find some differences between different compounds. The interesting thing is that she found that the disinfection byproducts that are actually regulated, so that have laws that limit their availability, are usually less harmful than the ones that are not regulated. So we might have to talk to some lawmakers and change that.
That will not be an easy conversation.
No, I'm sure. But nothing to worry about. The levels are very low as it is.
We don't have to fear our safety.
No, definitely not. I've been drinking tap water for years and I'm still sane and alive, so it's fine. And then Cameron has done a lot of biological growth experiments, so he looks at different fractions and which cause more growth. And he did see some differences there as well, which is very interesting.
Can I ask a question about this?
Sure.
You're saying about growth patterns. So basically, those microorganisms, you try to accelerate growth to see which kind grows faster, or how should I look at it?
So what we do is we split the natural organic matter into these fractions.
Yes.
Then we add a strain of microorganisms to those fractions. We incubate them. So we usually add a bit of nutrients. We make sure the temperature is perfect, that kind of thing. We know the starting amount of microorganisms. And then after a while, I think it's a few days, we see which ones have grown the most. We use a technology called flow cytometry for that. It's pretty new. It's not something we do research on. It's a different group that we work together with. And in flow cytometry, it's actually kind of light scattering pattern that measures how many cells are in a water flow. It's really cool. I know nothing about it, but they can basically make a fingerprint of the water and distinguish between different types of microorganisms even. So they can tell me, we've added this mixture of microorganisms. These microorganisms reacted differently than these ones, and that's different for each fraction as well. So it's pretty cool stuff.
It seems fascinating.
Yeah, it sounds really cool.
I love my job. I mean,
I can tell. Maybe going even a bit further, if I'm allowed. I know there's probably an intensive question and an extensive question, like how many microorganisms are in the water before they become harmful. But I can also assume that for some microorganism, it doesn't really matter if there's low doses. So how can you discriminate between those two?
You're asking difficult questions.
I'm sorry.
No, so I'm not a microbiologist. Let me make that clear. So I don't know. I don't know any numbers. I can't even give you a scale. I have no clue. The only thing I know is that our water is not sterile, but neither is bottled water. So with this flow cytometry, for example, they also made fingerprints of the different bottled waters that are available, and they could see different fingerprints in each of them. So there's different microorganisms in each of them.
That's actually an interesting point, because a lot of people think that drinking bottles are sterile.
Definitely not. That's the reason that once you open them, and if you leave them out, even when they're closed, air has gotten to it, you leave it in the sunshine, it won't stay healthy to drink because microorganisms will grow that were already in there, but now they get more oxygen and light and whatever. So no, neither tap water nor bottled water is sterile. We just make sure through treatment and through chlorine addition that it stays healthy and under control until it reaches your house and your tap.
Sorry, I didn't want to hijack Thomas's question.
I couldn't answer it anyway, so just...
Okay.
We'll leave it at that.
Okay. So now you're actually most of the time guiding PhD students. Do you miss working at the lab?
Yes and no, in the sense that I miss having control over the results. I'm a bit of a control freak, but I work with a lot of competent students, so that's pretty okay. But I also miss getting lost in the data. So one of the things I really liked during my PhD was having these massive Excel files full of measurements and data and whatever, and then trying to make sense of it and trying to find the patterns and trying to prove this is happening or this is happening, and then visualizing that. I really love that, and I still get to do it sometimes. I mean, when a PhD student gets stuck with their data, I try to help out, of course. But I also really like the guiding of the students, in the sense that it's very rewarding to see them grow and to see how they evolve in their own work. Actually, soon, normally before summer, the first PhD student that I'm officially a promoter of will defend her PhD. So it's something I'm really looking forward to. And that's something I didn't get to do as a PhD student, but I do get to do now. The problem is you can't do everything. So you're always going to miss certain parts. There's also parts of being a PhD student that I don't miss, like the insecurity and the trying to write a paper and getting it published part and stuff like that. I don't really miss that.
But as a postdoctoral researcher, you still have to publish, right?
Yeah, but I'm usually not the first author anymore. So I'm usually the one being difficult and giving a lot of comments on drafts of PhD students.
Oh, you're that guy.
Reviewer number 3. No. I try to be nice about it, obviously. But it's also fun to see, like, the student that will defend her PhD now. She's Bulgarian, so she might listen to this later. She's one of those people that would love for me to do more English science communication. But, I mean, she'll tell you the same. The first paper she wrote needed a lot of iterations, like going back and forth between her and the promoters.
Which is normal.
Yeah, it's very normal. It's the same for everyone. But when you compare that to the latest paper that she's published, it's day and night. There was a lot less input needed, a lot less comments needed. You really see that growth, and I love seeing that. I love how I can transfer my experience to a new generation of researchers.
Well, I have only guided some master students. I had like one really amazing master student that was a great experience, but I also had master students that really didn't evolve and they didn't improve, and whatever you did, it didn't help. How do you cope with that?
It's a very interesting question, because a month ago, we had to make the very difficult decision to stop the collaboration with one of our PhD students because he was actually in that situation. It's something I don't expect it ever would happen, but we had a PhD student working on a project with us, a very applied project with a company. I'm not going to go into too much detail. And he's a super nice guy. I really like him. He's very motivated. He's a very hard worker. That was never the issue. But he's just one of those people that starts a PhD. I mean, when you get into a PhD, you don't really know what you're getting into, right? You think research is cool, let's do this, we'll figure it out. But for some people, at some point, you just realize this is not for me. And with him, that was the case. The practical work, that all worked perfectly well. But when it came to scientific depth and really getting into the data and getting the science behind it, just wasn't his thing. It wasn't something that he was comfortable with. It wasn't something that he was really good at. So I think he'd be amazing working at a drinking water company, for example, and setting up new drinking water facilities, whatever. A PhD just turned out not to be for him.
He didn't like it, actually.
I think, especially towards the end, it was way too stressful for him. It was affecting him personally as well and emotionally, which is not something... I mean, to a certain degree, that's the same for everyone. But it got to a point where it wasn't sustainable anymore and it just wasn't healthy. And then we made the difficult decision of stopping the collaboration with him. So I think in the end, it's going to be the best for all parties involved. But it was a very hard decision to make.
Yeah, there's always a social and political weight in all your decisions, and
yes,
that can make it very hard.
Yeah, and especially in this case, it was a project with the company, so there was an expectation not only to deliver a PhD in the end, but also to deliver results and interpretations to the company, so that kind of made it a bit more high stakes, so to speak. But if you talk about master students, let's face it, some of them suck. That's what you were trying to say in very nice terms. But they all have to do it. If they want to graduate, you have to write a master thesis.
And let's be honest, for some of them, there's no ambition whatsoever to do anything in research. They just want to go to the job market and get a degree. So we should also put different standards.
Yes, that's true. And it can be frustrating as a PhD student guiding a master student, because if you have a good student, that work is also valuable for your PhD in the end. And if you have one that's, as Thomas puts it, his ambitions are not in research, they're just doing it because they have to do it, and that's it, they do the bare minimum, hopefully, then it can be frustrating. They don't adhere to deadlines, the writing is And as a tutor, you also feel a bit responsible for the end quality, which maybe we feel too responsible because it's their thesis, not our work. But it's very hard to distance yourself from that. One of the comments that my husband used to make and still makes, but now towards my PhD students, is that I'm way too emotionally involved. They're like my kids. And I had the same with master students and now with my PhD students. It's hard. There's always an emotional component to it, and there's always a hope that the data will be useful for yourself as well. But it's hard to make that distance towards this is just something they do to get their degree in the end.
I can imagine that it's hard when you're that involved, but it actually sounds like a good thing because you really care what's happening. So based on everything you're saying, I assume you want to stay in academia, right?
Yeah, I have to say that when I was finishing my PhD, I thought, nah, I'm just going to go into industry. I don't want to become a professor anyway. What am I doing here? And I recommend this to any PhD student or just starting professional listening. At some point, you really have to take a look at what is it that I like to do? What is it that I'm good at? Try to be honest with yourself. Like, okay, I suck at certain things. I'm good at other things. And then what do I need to do to be able to do the things I like to do and I'm good at, and not do the things that I'm not good at. We can't be good at everything. That's just a fact. And I've realized over the years that if I want to keep on doing the things that I like to do, which is stay in connection with research, guiding these students, in some ways you can do that in industry as well, managing a group and whatever, but also the science communication, the teaching and the really one-on-one guiding of researchers, that's not something I'll be able to do when I go to industry. Also the fast-paced but very flexible way of working, where if I don't show up to work tomorrow, no one's gonna care. As long as my work's done, if I'm not at my desk tomorrow, unless I have a meeting with someone that expects me to be there, no one's gonna care. I'm so used to that flexibility now, I don't think that's something I could handle going into industry.
But Marjolein, isn't it like a knife that cuts on both edges? Like this flexibility also makes that in the weekend, a weekend is just another day. Sunday, what is it?
Yeah, that's true. That's very true. Evenings, checking your email, you basically do it 24/7, right? If you're not being careful, especially as a PhD student, that's a big trap because a PhD you also do for yourself. You try to obtain a degree, so you are obviously highly motivated because you're doing a PhD. So then it's very dangerous to just work 24/7. I used to live 10 minutes by bike from where my experiments were. There were weeks where I was in the lab 7 days a week. And then at some point, my mom called and was like, "Are you still alive?" That's also something that I've had to work on over the last couple of years. Do you know what really helps to get that balance? have a kid.
Okay. Yeah.
Then you're forced to
I'll
focus
remember
on
that.
other things.
Yeah.
It's a cliche, but having a kid it really shifts your priorities.
Yeah.
It really changes your perspective. You love to, but you're also forced to give them attention.
Yeah.
So it really changes things. I still work. I officially work 4 days a week because I'm taking parental leave on Mondays. The funny thing is I've been doing that for a year and a few months now. And people are still surprised when I tell them I don't work on Mondays. They're like, oh, really? So apparently my output is still the same or something. That it's something to be mindful of, I would say. I mean, it's okay if you like to work 24/7. Just mental health is also important.
Very true. I think in general, when you have the loose schedule, people are tending to work more actually, or to work longer hours. And yeah, like you said, that's a real trap when you're doing research.
Yeah, that's true. I think the type of people that go into research are the types of people that with that flexibility work more. So yes, there's also people that would not be able to handle that and need the structure of you have to work from this hour to this hour, which is fine. I mean, everyone's different.
Yeah, of course.
But I think the type of people that go into research tend to work more when they are allowed to.
And is it actually the research, looking what's in the water and stuff like that you like most about working in academia?
Even as a kid, I was really fascinated by science and by the environment. So I was always the annoying kid telling everyone to turn off the lights and not let the water run while brushing your teeth or something.
I never understood that. People are doing that.
I don't think anyone does that anymore, right?
Yeah, I have never found anyone who said, yes, that's me. I'm letting the water tap open while I brush my teeth.
But maybe people used to. I don't know. But that's like the number one thing that people say, right? But like turning off the shower while you soap your hair or something.
Yeah, of course.
I was always that kid. I used to want to become an archaeologist because dinosaurs are cool.
That's true.
Or a teacher because I liked writing on a blackboard, which basically don't exist anymore today. So luckily I didn't pursue that. At some point I wanted to be a lawyer because people told me I was smart and had a big mouth. So that would be a good fit.
If that's all you need.
I think some TV shows also kind of influence that. But science has always been something I've been fascinated with. So my reason for going into academia has definitely been science. And it's still one of the reasons I'm staying. But one of the reasons I'm also staying is the passion I discovered while doing the science and the research. And that's the science communication. And management as well, by the way. Just organizing, managing, making sure everything runs smoothly. That's something I really, really love. And I love that in academia, especially like the further along you get, the more you pick what you do, basically. I pick my own hours. I get to kind of within boundaries choose what I do and what I don't do. For example, a few years ago, I coordinated the organization of the Young Water Professionals Conference in 2017. I was in Ghent. It was one of the most rewarding, amazingly fun things I ever got to do in my entire life.
Oh, really? I already hear people complaining about organizing stuff like that.
Pay me to organize conferences and I will do it for you.
Okay.
But is it because you see something tangible coming out of it? Like, you work to it and you have like relatively close already the payoff. Well, many things in research, it takes a long time before you have the payoff.
Yeah, I think so. Part of it's definitely that. It's also the control freak in me. I was really coordinating it. Like I had the overview of what needed to be done and I checked up on people if they were doing it. And part of my job, and that's shown through there, but it's true every day, is being a pain in the ass. Making sure people do things. Apparently I'm good at it, so that's fine. So part of it is definitely the tangible stuff. I've never been as tired as I was at the end of that. Well, that's probably not true anymore. I have a kid now. Yeah. But before that, I had never been so tired and so fulfilled, and it felt like such a reward when the conference was over and everything ran smoothly. And I basically spent all of those days running around, fixing little problems, and I loved that. But discovering that that's something I'm good at and I love doing, I really believe that's something that I could only have done because I was in academia and I got the opportunity to do that. I can't imagine in a company they would ever, without even consulting my boss, someone would ask me, hey, do you want to coordinate the organization of this event for 100 people of 3 days long? Like, sure, go for it. So yeah, that's one of the things. One thing I would like to add, and it's been in the back of my mind throughout our discussion the last 10, 20 minutes probably. One of the things that I really like about academia is I believe there's ups and downs to every job, definitely. I just really think that the ups are way higher. The downs are probably also way lower in academia than in industry. Like that moment you publish your first paper
that's an amazing feeling.
It's amazing. Yeah. Or when your first conference presentation goes well, or you win an award with something or whatever, those are great highs. The moment when someone calls you on a Saturday morning telling you your experiment that's in the middle of running supposedly 12 days, but you're on day 6, is now flooding the lab, those are the lows.
Yeah. It sounds like a really specific example, like something really happened to you.
It did, and it contained pharmaceuticals and everything, so it was a lot of fun to clean up.
I can imagine.
I cried. I'm not afraid to admit I cried. I went to the lab, I sat down for 10 minutes and then started cleaning up. Yeah, no, but that's something, I don't think that's for everyone, but it's something I really enjoy. And I get to live through my students as well. So yeah, that's what I like about being in academia.
Like you said, you also really love the science communication.
Yeah.
You also have written your first book. Must also have been really exciting. Unfortunately, it's only in Dutch, if I'm not mistaken.
Yes, it is.
So far, maybe? I don't
know. Who knows? I have a Chinese colleague who keeps telling me, if you translate it to English, I'll translate it to Chinese. So
so you already have opportunities stacking up.
Yeah, I guess. There was a very deliberate choice to do the science communication in Dutch, because I feel like there's still a lot of work to do when it comes to water awareness in Flanders. And then if you then do science communication in English, you're not going to reach your target audience. So the podcast is in Dutch, the book is in Dutch. That's a deliberate choice to reach the target audience I want to reach. A little bit about the book maybe as well is I only wrote very little of it in the sense that it has 2 authors, right? It's me and Toon Verlinde. The idea for the book was Toon's. He's one of the founders of The Floor is Yours.
Yep.
A company that helps researchers convey their research in an understandable way. He does a great job there. But he also has a background in water. He used to work for an NGO doing water projects in Africa, stuff like that. And he really wanted to write a book. And he knew me through the Sound of Science Festival was one of the things. He organizes it together with Hetty Helsmortel. I know Hetty because she used to be at Ghent University. And yeah, we kind of knew each other through that. And he had seen some of my stuff. I followed a workshop with them. Anyway. And at some point he emailed me like, hey, I want to write a book. I want to do it on water, but I know that's your thing. Are you like already doing something like that? Do you want to cooperate? So it was his idea. And the moment he asked me, I think I was 2 or 3 months pregnant or something. So I was like, let's brainstorm, see what happens. And most of the book was written while Louis, my son, was just born, I think. So, I mean, no way I could do a lot of it. So the things I did was mostly provide contacts. He went to talk to a lot of people in the drinking water companies, some people from Capture in research. I made most of those contacts possible. I wrote some parts, like the parts on the water footprint, the part on seawater desalination, some parts on groundwater, that kind of thing. I reviewed everything. I gave comments on everything. We had a lot of discussion. But Toon was definitely the main writer of all of it. And it was his idea. But it's still very cool to have your name on a book and be an author. So that's kind of how the book came about.
Must have been a great feeling, like your first paper, but then your first book.
Yeah. To have it, the physical copy.
Yeah.
It's like, yeah. I mean, having the physical copy of your PhD is cool, but I must admit, this is another level of cool in the sense that you know that a lot more people are going to read it.
Yeah. Your PhD, that's like the jury members reading it, and that's more or less it, right?
Yeah, hopefully some people in your field will read the papers that are in the PhD.
Yeah.
Yeah.
So, but in science communication, you also have lectures, or should I call it shows? I don't know what you prefer.
I think shows is a bit of a big word. I don't think it's much of a show. I don't know what the right English term is. Like in Dutch, you would say, I give lezingen.
A lecture, maybe?
Yeah, it's kind of a lecture in front of an audience of the general public.
A fun lecture.
Yes. Something people come to learn. Infotainment. Is that what it's called?
That's a really good term. Did you make that up right now?
No. I think it exists. But
okay. I never heard of it, but it's really good. Infotainment.
Yeah, I do that too. That's true. Mostly in front of groups of retired people.
Ah, really?
Yes.
It makes perfect sense, right? They have the time.
Yeah, and I can perfectly imagine myself sitting in that audience when I'm retired.
And is it basically that you don't need any prior knowledge to understand these lectures?
Yes.
Okay.
So it's very low level.
And what do you talk about in these lectures? Oh, you have to go watch the lecture to know.
Yes. No.
Okay. Well, for the English-speaking people, it's a bit harder. It's in Dutch, so...
Yeah, that's true. So it's actually evolved a lot over the years. As I said, the most sexy part of my PhD was the part on seawater desalination. So the first times I was asked to come give a lecture or talk about something, it was on that specific topic because that's what they knew me from. But then based on comments I got, and especially questions from people, I noticed that most of them were really interested in, okay, but the drinking water that comes out of that, is that safe? How do we do that? How do we transport it? Where else can it come from? It was a lot of prejudices, a lot of knowledge lacking on the drinking water system in Flanders. So over the years, it has slowly transitioned from how do we do seawater desalination and should we do it in Belgium to this is how the water system in Belgium works. And maybe at some point we'll desalinate some seawater to get drinking water. That's basically now it. So since the book, Toon and I also made a presentation, a lecture on the book itself, which is kind of a show, especially when Toon gives it, is much funnier than I am. The main premise, and if you have a look at the book, there's this schematic, this cartoon in it that has like a blank square, a rain cloud on one side and a tap on the other side, and then it says, I don't know what happens here. The main goal of the book is to kind of give you an idea what happens in between the rain and the tap and how that happens in Flanders. And that's, depending on how long the lecture is, I try to take people through that history and through that whole process. That's kind of the idea.
Well, that's already a nice visual or a nice image to have the cloud and the tap.
It's easier to see it than to explain it in audio, but...
Yeah, I can. So, yeah, we actually talked already that you wanted to do science when you were a kid.
Yep.
Or you were very interested in science. Why did you choose not to work on dinosaurs? Because you love them so much.
I think that came about when I got more and more concerned about our environment. And especially the older I got, the more environment switched to climate change, which is two very different, although interlinked things. And that's how I ended up choosing to become a bioscience engineer, because then you still don't really have to choose what you specifically focus on. And then, but it's always been clear that I would go into environmental sciences because of that. I've always been very sensitive to what happens on our planet and the environment itself. So by the point I had to choose what I was going to do at university, it was very obvious that that's what I had to do.
And does some of your work also touch on climate change or not really?
It does, in the sense that the reason I have a lot of work at the moment is because of climate change, in the sense that water and climate change are intrinsically linked. You can't look at one without looking at the other. If you're living in Belgium, you know that 2018, 19 and 20 were ridiculously dry years because of climate change. That affected our water supply. And then 2021 affected our water supply in the opposite direction, in the sense that we had a lot of flooding. But that also causes issues with water quality, for example, because, yeah, a river floods and then drags along all of the crap, and then the river quality is much lower. So I don't do climate change research. There's plenty of very capable people already doing that. But I try to do my part with the water research. And I mean, doing research into more efficient, more energy efficient systems is a very big part of that. And also now, maybe that's interesting to mention as well, we are venturing more and more, and that's not me, when I say we, I mean Capture and the whole consortium, into research into the hydrogen economy. Because what people tend to forget is to produce hydrogen gas, you need very clean water and you need a lot of it. So that's the research that we are now venturing into, like how can we efficiently produce that water? What technologies are needed? How clean does it really need to be? Can we use waste streams from somewhere else? You don't want your drinking water supply to be affected by that. Energy and water are also very linked to each other. So that's something that we're now looking into. So no, I'm not directly involved in climate change research, but indirectly I kind of am.
Okay. And if you weren't a scientist, do you know what you would be then?
That's a good question. I haven't thought about that in a long time. I'm not sure what the answer would be today.
Maybe a lawyer?
Nah, I'm way too nice to be a lawyer.
I think I'm going to cut that out.
Do you know any lawyers that would get mad at me? No, I think I'm too emotionally involved to be a lawyer. I think with any client I would just be very sad if I couldn't help them or something. No, I actually know what I would be. Something else that I'm very interested in, and also related to climate change, but to science in general, is psychology. It's actually one of the studies I also considered. And what interests me a lot is why people believe completely unscientific, ridiculous things. And then most importantly, how you can convince them of the more scientific, logical things. So I think that's what I would study if I wouldn't be a scientist.
But it's again from a science perspective.
It's really science, yeah.
Yeah, but no.
It's fine, but it's interesting.
It's a different field.
Marjolein, you mean like, for example, people who believe in conspiracy theories?
Yes.
I felt it was that. I felt it.
Like, why the hell would you believe the Earth is flat and thousands of people need to be in on it rather than just accept that there's a picture of a round Earth?
Well, I saw once like a guy who was going to prove that Earth is flat, and he just took a level with him on a plane and it stayed level. And he says, look, Earth is flat. That's not how a level works.
That's not how it works.
No.
There's actually a very good documentary on Netflix on flat earthers. I'm not sure what the name is anymore. Yeah, the fun thing is the ending, which I'm kind of going to spoil. So if you don't want to hear this, like fast forward a bit. But they kind of set up an experiment where they're going to prove the Earth is flat. And they actually accidentally prove it's round. I loved it. I loved it. It was,
As
it
it
was
should
great.
be.
Yes. But it really intrigues me. Like, I try to realize every once in a while that we, like the three of us sitting here, we're very privileged. We live in a world of scientists. We don't have to convince anyone of the scientific methods. But we are a very small minority. The average person on the street doesn't have time to be concerned of doing their research, and they just read something and take it for granted, or they listen to the news or some wacko on YouTube and assume that they sound credible. I'm sure they're true. Vaccines cause autism. I'm not gonna vaccinate my kid. That's it. So I try to like think about that every once in a while.
That's one of the good things of science communication.
Yeah. So that's one of the reasons I'm into it.
But in a sense, it's also a trap, right? Because recent science on vaccine hesitant people has shown that you cannot convince them by giving them more facts.
I know.
So this is quite frustrating. You know, you have to go around to the emotional path somehow.
Yes, but how do you do that?
That's why you have to study psychology.
Yeah, or marketing. I've dabbled in it a bit where I've helped marketing students set up campaigns around water and whatever, but it's not big campaigns or something. I would love to set up a project with the drinking water companies and a big marketing firm or something. Bottled water companies have very big marketing budgets. Drinking water companies do not.
Maybe to end on a happier note, do you have maybe a take-home message for the listeners?
Does it have to be water related?
It doesn't have to be.
If it doesn't, then I'd like to go back to the discussion we had on why do you do what you do? And my take-home message for everyone listening would be, don't only do what you feel is expected from you, but take a hard look at what is it that I actually like to do and what is it that I'm actually good at, and try to work towards doing more of that. And I'm sure you'll be a much happier person.
That's a really great sentiment to take home.
I kind of stole it from, I didn't steal it, but it was inspired by the autobiography of Michelle Obama, because this is a process that she also went through in her life. And I think it's very inspirational, and I think it's something that our lives kind of get lived through what people expect from us. And if we just take the time to stand still every once in a while and take a good hard look at what am I actually doing, I think that would help a lot of people.
Okay, sounds really good. So for our Dutch-speaking listeners, I would recommend to listen to the podcast Helder by Marjolein and read the book Weg van Water. This was the 4th episode of Apple Finch Pudding. I want to thank Marjolein for the information and Thomas for the additional questions. Let's meet again for the next episode of Apple Finch Pudding.